Question number 31. Two wheels A and B of a machine rotate about a common axis in the same direction with angular speed omega 1 and omega 2 respectively. See figure A. Moment of inertia of wheel A about its axis of rotation is I1 and that of wheel B is I2. At a certain instant, two wheels are pushed towards each other until they are firmly fixed and system rotates with the common angular velocity. System rotates with the common angular velocity omega without slipping. See figure B. The value of omega is given by. We can use the conservation of angular momentum. Both wheels are rotating in same direction before the collision. Therefore, we have to add angular momentum I1 omega 1. It is the angular momentum of A. Then I2 omega 2 is the angular momentum of B. This is the sum of angular momentum before the collision. We have to add because of there are angular velocities in same direction. Then it should be equals to final angular momentum. When considering final moment of inertia, we have to add moment of inertia values of both wheels I1 plus I2 into omega is the final angular velocity. Then we can subject omega I1 omega 1 plus I2 omega 2 divided by I1 plus I2. It is the angular momentum of the system after the collision. Then we can get fourth answer is the correct answer for question number 31. Then question number 32. A thin ring of mass m and radius r is rotating in a horizontal plane about an axis passing through its center perpendicular to the plane with a constant angular velocity omega. Now if two small masses, each mass m are attached gently to opposite end of diameter of ring, the new angular velocity of the system is. Again we have to use the conservation of angular velocity, conservation of angular momentum. The angular velocity of the ring before connecting two masses is omega, and after connecting two masses we can consider angular velocity is omega dash. Now there are simple limb masses. Then we can get I1 omega 1 equals to I2 omega 2. I1 omega 1 equals to I2 omega 2. Conservation of angular momentum. Angular momentum before the collision equals to angular momentum after the collision. Collision means after connecting two simple limb masses. Then I1 value is mr square. We know that if the mass is capital M and radius of ring is capital R, then moment of inertia of the ring is mr square into initial angular velocity omega should be equals to, when getting final moment of inertia, we have to add mr squared and 2 times simple m r squared. Simple m r squared is the moment of inertia of one point mass. Then we have to multiply by 2 to get the total moment of inertia of simple m masses. Then I will consider final angular momentum omega dash. Then we can simplify it. We can cancel out one r term. Then we can subject omega dash m omega divided by capital M plus 2 simple m. M omega divided by capital M plus 2 simple m. Then answer is 1 for the question number 32. Then 33. A traditional grain grinder consists of two flat stones. The upper stone is rotated on the top of lower stone, stationary stone, by applying a horizontal force of magnitude F to the handle capital H, which is fixed at a distance simple r from the axis of rotation as shown in the figure. if the force is always applied parallel to the direction of motion of the handle and the period of rotation is t, the power being expended is, we have to find the power. We know that when getting work done by a force, work done W is force into distance. Now we can get power. Power means work done per second. Then we have to divide both sides by time. This is the power. Power should be equals to force into x over t. X over t means distance divided by time, it is speed. When considering full rotation, we know that period is the time. It is equals to 2 phi r divided by velocity. This one is the velocity or speed. We can consider it as speed because of the direction is changing always. We can subject v, speed, from this equation. V equals 2 phi r divided by t. Then we can substitute v value to the power equation. Then power equals to force into 2 phi r divided by t. F into 2 phi r divided by t. Then answer is 2 for the question number 33. Then question number 34. A wheel starting from rest is allowed to roll down without slipping along an inclined plane as shown in the figure. Which of the following graphs best represent the variation of the magnitude v of velocity of point P located on the perimeter of the wheel relative to Earth with time t? Within the bracket they have given that the point P touches the inclined plane at t equals 0. When getting this motion, we know that the point P getting a maximum speed relative to Earth at this place because of it is moving at a pace like this, because of it is moving horizontal to the moving parallel to the Earth surface. Therefore, when considering the velocity relative to Earth, it has maximum value for this point. Then we have to consider the time taken to come point P to this place. Initially, P is touching the inclined plane. Therefore, we have to consider the time taken to get the displacement, which is equal to this point to this point. Then, after the first rotation, it is always getting a constant time to get the maximum velocity approximately. Then we can get initially this P should be moved to this place to get the maximum velocity like this, and relative to Earth it is decreasing after passing this point. And then for the second situation it takes a short time to get maximum velocity. After the second time it takes third maximum velocity at this place. Then we can consider graph is 5 for the question number 34. Then 35. The variation of the angular acceleration alpha of the wheel of a motor vehicle starting from rest with time t is shown in the figure A. Variation of the angular velocity omega of the wheel with time t is best represented by. They have given angular acceleration graph. We have to find the angular velocity graph. We know that gradient of angular velocity graph is representing angular acceleration. For the first situation, there is a constant angular acceleration. When considering angular acceleration constant, therefore angular velocity time graph should be like this. It has a constant gradient. Then for the second situation, it has a minus angular acceleration. Minus angular acceleration. In the omega t graph, it should be like this. There is a minus gradient. Angle between plus direction of x-axis and graph is an obtuse angle. Then for the third situation, angular acceleration is a plus constant, but it is greater than first value. Therefore, for the last situation, gradient of the graph should be greater than this graph. It means it should be with a high, with a greater angle than this. Then we can get third answer is correct answer for the question number 35. Then question number 36. A child is standing at x equals minus r of a horizontal merry-go-round of radius r in carnival as shown in the figure. XY coordinate system fixed to the merry-go-round with its y-axis along the axis of rotation. Using a driving motor, the merry-go-round is set in rotational motion with constant angular velocity omega naught about its axis on the frictionless bearing and subsequently allowed to rotate freely without driving motor. Now, if the child starts to move the x direction along the diameter of the merry-go-round to location x equals plus r, the variation of the angular velocity omega of the merry-go-round with position x of the child is best represented by. We know that it is rotating with a constant angular velocity. Child is at this pace and he is moving along the diameter. We know that there is no an external unbalanced torque on the system. Therefore, angular momentum should be conserved. Then, when the child is moving from this point to center, moment of inertia of the system is decreasing because of the mass spreadness is decreasing. After passing center, again moment of inertia is increasing. When increasing moment of inertia, we know that angular velocity is decreasing. When decreasing for this part, moment of inertia is decreasing, angular velocity is increasing. And after passing center, angular velocity is decreasing. Therefore, graph should be like this. Then we can get second answer is correct for the question number 36. Then 37. A uniform disk of mass m and radius r rolled without stripping initially along the horizontal surface and subsequently start to climb up a ramp as shown in the figure. The disk has a linear velocity omega on the horizontal surface. It should be the moment of inertia of the disk about the axis to its center, and normal to the plane of disk is mr squared divided by 2. What is the maximum height to which the center of mass of disk climbs? We have to use the conservation of energy. When considering conservation of energy, initial kinetic energy should be equal to final potential energy of the system. But initially, the disk is rotating. Therefore, there are two types of kinetic energy. It is a rolling motion. Therefore, there is a kinetic energy. It is half mv squared. It is the linear kinetic energy. We can consider the rolling motion is the sum of motion of slipping and rotating. Then when considering rotational kinetic energy, it is half I omega square equals to potential energy mgh. Now we have to substitute moment of inertia and omega value. They have given that moment of inertia is half mr squared, and we know that v equals r omega. We can subject omega from this equation v over r. Now we have to substitute these two terms. Then half mv squared plus half I value is half mr squared into omega value is v over r. we have to use the square term, omega squared. Therefore, we have to use omega squared over r squared equals mgh. Now we can cancel out r squared in term form of all terms. Then we have to simplify. 1 over 2 means 2 over 4 v squared. 1 over 4 v squared. After adding, we can write 3 over 4 v squared should be equals to gh. Then we have to find the h value. H should be equals to 3v squared over 4g. Then 3v squared over 4g is third answer for the correct answer. Third answer is the correct answer for the question number 37. Then 38. A boy sitting on a smooth turntable with a weight in each extended hand is rotating with an angular velocity omega naught. When he bends his hands towards his body, the angular velocity becomes omega 1. If I naught and I are moment of inertia of rotating system when the hands are extended and bent towards his body respectively, then we have to get the relationship omega for omega I and I omega product. First of all, we have to understand that when bending his hand, moment of inertia is decreasing because of the mass spreadness is decreasing. Then I1 should be less than I0. I1 should be less than I0. When decreasing moment of inertia of a system without any external unbalanced torque, its angular velocity should increase because of we have to use the conservation of momentum, conservation of angular momentum. When decreasing I value, omega 1 value should be greater than omega naught value. Finally, there is an unbalanced external unbalanced torque. Therefore, I1 omega 1 product should be equals to I2 omega 2 product. Then we can get answer is 3 for the question number 38, but there is an error in the PDF because of they have given that I0 less than I0. It should be I0 less than I1. I0 is greater than I1. It means I1 is the small value. 39. 3 identical uniform metal discs are performed to form 12 holes in each disc with 3 different radii shown in figure A, B and C. The 3 discs A, B, C when arranged so that their moment of inertia about axis normal to the plane of the disc and passing through center are in ascending order. We have to select ascending order of moment of inertia. Then considering holes in figure B, large holes are near to axis. It means its spreadness should be, its mass spreadness should be the greatest value. Then greatest moment of inertia should be B. We can get logically like this. The smallest moment of inertia should be A. Then we can get A, C, B order. Answer is 4 for the question number 39. Then question number 40. A uniform solid wheel rolls along a flat surface at a uniform velocity v without slipping as shown in the figure. P is a point on the circumference of wheel. Location of point P at t equals 0 also shown in the figure. Variation of horizontal component of velocity Vx of the point P with respect to surface with time is best represented by. We know that when considering rolling object, velocity of all points should be v for a slipping object. If it is rotating, velocity should be like this. And we can get sum of these movements should be equals to rotation, should be equal to rotation. Then V plus V 2V, we have to get component resultant force for these two resultant velocity for these two velocities. It should be a direction like this. When considering these 2 points, velocity should be 0 at this point. Then again we have to get resultant at this place, this point. Now you have to select variation of horizontal component of velocity of point P. It should be 0 for the initial value, it is at this place. And it is increasing with to a maximum value and again decreasing to a small value. The small value is 0. Then graph should be like this. It is increasing and decreasing. The graph should be 1 for the question number 40. When considering horizontal component, it is always in this direction because of it should be a positive value. It means the graph is always varying in positive direction. Then answer is 1 for the question number 40.